we've got gases, so things may look a little different, but they're not necessarily going to be. If we look back at our mole map, if we have a gas at STP, we can go this way. If we're solving for a gas at STP, we go this way. A gas that's not at STP and we have a volume, we're going to take pressure and volume divided by the ideal gas constant and temperature, and we can solve that direction as well. We can also end up down here with grams, or we could start with grams. There's lots of different things we can do. So here we go. Question number 14. Our equation's given to us. It says, what mass of water vapor is produced? So we're solving for mass. That means we're going to end up down here on our map, our bridge. And we're given volume of propane with a temperature and a pressure. So let's start with what we know. 3 liters. Well, first of all, I better write PV equals nRT. If we solve for number of moles, we're going to do pressure times volume over the ideal gas law times temperature. The pressure given is 0.97 atm. I'm going to go ahead and set it up real fast. The volume is 3.0 liters. The temperature is 23 degrees Celsius. But wait, don't forget we have to change it to Kelvin. So we're going to divide by 296 Kelvin, and then the value for R, 0.821 liter atmospheres over mole Kelvin. Kelvins cancel, liters cancel, atmospheres cancel. And that will give us an answer in moles. Okay. All right. Now, even though I'm not technically wanting to work these out, I'm going to give you guys this answer next time. I'll run them all in together. 0.1197, which I'm going to round to 1, 2, because 2 sig figs. But again, you're not worrying about that right now. So now we're on the bridge. This is our known amount of moles. We're going to solve for mass of water vapor. We're here, and we want to go to here. So the mole ratio is 1 mole of C3H8 to 4 moles of water. And now we're on the other side of the bridge, and we want to change to grams. And the molar mass from water is 18 grams in 1 mole. Okay? Number 15, we are solving once again for mass of iron, and we're given volume, temperature, and pressure. So once again, we're going to do PV divided by RT. The pressure is 0.95 atmospheres. The volume was 2 liters. 0.0821 atmospheres times liters over mole Kelvin. And temperature is 75, I'm going to write up here, 75 plus 273, 348. All right, so we've now gone to moles. I could hit equal and do the math, But I can also keep going, just like we have done with our other equations. When we get to moles here, when we get to moles here, we don't stop. We go ahead and multiply by the ratio. So that's what I'm going to do. We are solving for iron, so that's our unknown. And we started with hydrogen gas, so that's our known. So now we're in moles of iron. We want to change to grams, 55.85 grams in 1 mole. Okay, and that's what you do. 16, we know the volume and pressure and temperature, and we want to solve for mass of sodium azide. Sodium azide is NaN3. And we're solving for nitrogen. We want to we want to know how much azide it takes to blow up our nitrogen bag, our bag full of nitrogen. All right, so once again, PV over RT, we're going to do 75 liters times 1.3 atmospheres, 0.821 liter atmospheres over mole Kelvin. 25 plus 273 is 298 Kelvin. All right, next up would be the ratio. We are starting with nitrogen. 3 moles of nitrogen will require 2 moles of sodium azide. And then we need to multiply by the mole mass. Number 17, we're starting with grams. This one's out of place. This should have been back at the beginning. Oh, no, I lied. We are doing volume. So this is a gas one. We're solving for volume. Okay? We want to know how much hydrogen we're going to get. But we know 4.73 grams of magnesium and 1.83 grams of water. So what do we do when we have amounts of both of our reactants? Well, we have to solve for limiting. So we'll start 4.73 grams of magnesium divided by 24.31 grams in 1 mole. The ratio of magnesium to hydrogen is 1:1. 1 mole of magnesium will give me 1 mole of hydrogen, and it's at STP. So I can now use the upper left-hand corner of my mole map. I've now it wants to know where we're going to move from moles to volume at STP. So we're going to multiply by 22.4 liters per mole. Okay. Next one, 1.83 grams of water, because remember, we're doing limiting. We want to figure out which one will be smaller. That will be our limiting factor, and that will be the maximum amount of the gas we could produce. Even though the other number is bigger, we wouldn't ever get there because we'd run out of the limiting one. Water's molar mass is 18 grams. The ratio of water to hydrogen, 2 moles of water to 1 mole of hydrogen. And again, it's at STP. So we set that up like that. Last guy, we are given volume, temperature, and pressure. So we're going to use PervNERT. And we're going to solve for volume of oxygen. So 3500 liters of carbon monoxide. And we need to do PV over RT. 1.04 ATM. 0.0821 liter atmospheres over mole Kelvin. And 30 plus 273 is 303 Kelvin. Okay, we're in moles of carbon monoxide. We need to figure out oxygen. Our ratio is going to be 1 to 2. 1 mole of oxygen gas for 2 moles of carbon monoxide. Now we're in moles of oxygen. I need to go back to volume. So I'm going to use PV equals nRT, but this time I'm going to solve for volume. So we're in moles. That means I need to multiply that times 0.821 liter atmospheres over mole Kelvin times temperature, which we said was 303 Kelvin, and pressure, which is 1.04 atm. All right, there you go. Have fun.